Well, good afternoon. I'm sorry I'm about 7 minutes late getting started, but I got to the classroom, nobody was here, so I thought, well, let me run down to the restroom, get a drink of water, and clear my head one last time. And I happened to see a biology instructor in her office, and she said someone had stolen the projector cord in the room she was teaching, and what did she need to do about it? She's an adjunct instructor. So I had to get it down for her because she needed to return it. And so that took the extra minutes. So sorry I'm late getting started. But let's go from the current slide. Obviously, I'm the only one in the room now. I'm talking to the screen. And we are in, I can't see well enough. Now the leaves are out in the tree. I don't get as much natural light in the room as I did. It's fine, but can't see as well. So we're in Chapter 4, Higher Order Differential Equations, 4.3, Homogeneous or Homogeneous Linear Equations with Constant Coefficients, on page 137, getting ready to do Example 1. Okay, we led up until this last time, so let's do the Example 1. Now, all right. This is based on the fact, now that I recall, I think we got last time I think we did the superposition principle, theorem 4.1.7, and I think we got down to example 11. Now, and I believe I asked you to cover on the YouTube videos the next video, okay, which I think went through this. Well, in my first two classes today, a total of 0 students saw the videos, so I don't think I probably should be able to, or should, assume that y'all saw the videos too. So I'm going to go back and like I said, I think we did example 10. I believe we were down to example 11. So I'm going to go back to 4.1. Again, Chapter 4, Higher Order Differential Equations, 4.1, Preliminary Theory Linear Equations, on page 129, and do example 11. It says you should verify that y sub p, let me get my pen set up. All right. Y sub p1 is equal to minus 4x squared is a particular solution of y triple prime minus 3y prime, oh, I'm sorry, that's y double prime. My eyes aren't good today. Sorry about that. Okay, y double prime minus 3y prime plus 4y is equal to minus 16x squared plus 24x minus 8. Okay? It says that this is a particular solution of that. All right? Well, we need to verify it. Okay? So what we'll do is do a y p1 prime. That would be equal to minus 8x. 2 times minus 8x. And yp1 double prime is equal to minus 8. Okay? So let's plug those in. Minus 8, that's yp1 double prime, minus 3 times y prime, and that would be 3 times 8, that would be minus 24x, okay, plus 4 times y, that would be now a plus 4 times a minus 4 would be, oops, wrong thing. Okay, that would be a minus 16 x squared. And sure enough, those are equal. Those are equal, I mean, whoops, messed that one up. Oh, it's a minus 3 times a minus 8, that's a plus 24x. Got it. And those two are equal. Okay? So, yep, that works. Okay? We verified that is a particular solution for that differential equation. Okay? We also want to know that yp2 equal e to the 2x is a particular solution of y double prime, all that's the same, okay, and this is equal to, when it's equal to 2e to the 2x, okay? Well, let's do it the same. Y prime of p2 is equal to 2e to the 2x, and y double prime sub p sub 2 is equal to 4e to the 2x. So if you plug those in to the same equation here, that would be 4e to the 2x minus 3 times 2 is minus 6e to the 2x plus 4 times that is plus 4e to the 2x. Sure enough, 4 and 4 is 8 minus 2 is 6. That's equal to e to the 2x. So that works. They also said, verify that y sub p3 equal xe to the x is a particular solution of this same thing, but now set it equal to 2xe to the x minus e to the x. Okay? This is such an aggravating program. So we're going to need to do a yp3 prime, and that's a product rule here, so that's going to be first times derivative of the second, that's xe to the x, plus the second time derivative of the first, e to the x. And y double prime p3 is going to be same product rule before. That would be xe to the x plus e to the x plus another e to the x, so it's plus 2e to the x. Okay? One from the derivative of this one and one from the derivative of that one. Okay? When you plug that in, 4 times, y double prime is, I'm going to start over here, xe to the x plus 2, that's an ugly 2, let me clean that up a little bit, okay, plus 2e to the x minus 3 times, that would be minus 3 xe to the x plus 3, or minus 3 e to the x. All right. Plus 4 times y, that's plus 4x e to the x. The question is that equal to this 2x? Okay, let's see. Here we have x e to the x minus 3x e to the x plus 4x e to the x. That would be 4 plus 1 is 5 minus 3 is 2 x e to the x, so that works. Okay, and here we have a 2e to the x, and that took care of that one, and that one. Minus 3, so that'd be minus e to the x, minus e to the x, and sure enough, that is that. This is that, that's that. Yes, all three of these work. Okay? They solve that. They are particular solutions for the three. The homogeneous parts are the same for all three. It's the constant, not constant, it's the functions that on the right-hand side that are different. So same differential equation, but equal to three different things at the end. So it follows from this, and from your theorem 4.1.7, which we did last time, that if you have a sum of these three particular solutions, this one plus this one plus this one, will be a solution to this differential equation plus this plus that plus that. You know, when those three are added together. Okay? So I'm going to go to a clean slide so I can write this in, but you have to remember what's on this slide. Hopefully you have it. So let's see what we've got. And this is using your superposition principle. Those three particular solutions for those three different sets of functions after the same differential equation on the left-hand side. Now, I wish they had said this was y sub p. I don't like for them to call it y because that seems to imply that's your total solution, but it's not. I'm going to call it y sub p is equal to y sub p1 plus y sub p2 plus y sub p3, okay? And that will be the sum of those three ones minus 4x squared plus e to the 2x. See, I don't have it written down. I have to read it from the book. Plus x e to the x, okay? So this will be a solution, a particular solution to the differential equation that starts just as before, y double prime minus 3y prime plus 4y is equal to minus 16x squared plus 24x minus 8 plus 2e to the 2x plus 2x e to the x minus e to the x. Okay? Now, that differential equation, same as the other. The one that produced yp1 was this one. The one that produced yp2 was this one. Let me do this in a different color maybe. Yp2 was this one, okay? And then the one that produced yp3, let's make that orange here, that was this one, okay? So since each of these was a solution to one of the differential equations, the sum of these solutions would produce the sum of those there to being a particular solution for this differential equation. That's what the superposition principle tells us, okay? So basically, but not just that, let me go back to black here. What's more, and this is also said in theorem 4.1.7, it's not just that those form, but that a particular solution y sub p is equal to c1 y sub p1 plus c2 y sub p2 plus c3 y sub p3, and if you kept on going, plus dot 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 plus c sub k, I believe they use for this one, yeah, y sub p sub k, okay? That your particular solution would be any linear combination of any of these. So the one we just did, it doesn't have to be these. It could be any linear combination of C1 times this plus C2 times this plus C3 times this one. Okay? Will also be a particular solution. Okay? Now, they say they need one additional bit of theory, which is presented in the next section, and that's what we're going to do next. Now, if I didn't stop and tell you before, homework exercises here for 4.1.1, which you've had quite a while now, are either 1 or 3 or both if their answers are in the back, and either 5 or 7 or both if those answers are in the back. 9 if that answer is in the back, 11 if that answer is in the back, 13 if that answer is in the back. And 4.1.2, which we've now finished, any of the odds 15 through 21 if those answers are in the back, any of the odds 23 to 29 if those answers are in the back. So we had finished those before, sorry. 2.1.3, which we have now finished, is either 31 or 33 if those, answers are in the back, and 35 if that answer is in the back. And here's Danny. Okay, good to see you. I'm tired of talking to you. Okay, I'm not even on the right page. That's how tired I'm talking to myself. Okay. So Dan is here. And this is 15th, 17th. That's all we really need here because other classes don't meet these days. All right, let me turn on. Now, did you look at the videos for Wednesday? I did. Okay. Of my 3 classes that I've had today, not a soul did, so I just went back and started where I left off before. Because if I started the next place, I think you'd be lost because it depends on the stuff that's there. But don't worry, not another student in any of the classes did watch the videos. So it's all a good idea, but it was all just why the vice president said, make assignments. So I did. All right, what we have here, what we did at the end last time, now my memory anyway is that we got theorem 4.1.7 done at the bottom of page 128, but we hadn't done the example 11. Okay, I just finished 11. Okay, so you can see that on the video. This is the second screen of it. But basically, we verified that the 3 particular solutions were equal to this differential equation, set first equal to that. That was the P1, which I have, oh, there it is 4 minus 4x squared is a particular solution, and that is your right-hand side. When 2x to the 2x is, that satisfies when your right-hand side is e to the 2x. No, I'm sorry. E to the 2x is the particular solution that satisfies that. And let's see, I lost something in translation here. There's a C up here that didn't show up. Okay. And when that is your particular solution, when this is your right-hand side. So therefore, if all three of these are on the right-hand side of that differential equation, a superposition of all those will work. And they just happen to say that sum of those three works, but not only that sum, any linear combination of those sums works. Okay? In general, if you have a particular solution, well, if you have k particular solutions for one given differential equation, okay, phrase it another way. You have a given differential equation here, the homogeneous part, but the non-homogeneous part, you have a series of things. Now this is a polynomial. You can group those together. This is terms with e to the 2x in them. Can't mix those with those. These are terms with e to the x in them, so you can put those together. Okay? And if you can come up with a particular solution that works for this one, that works for that one, works for those independently, then any linear combination of those three, or any others that you have, up to k of them, any linear combination will be your particular solution of that. Now this is a particular solution for the non-homogeneous case. The homogeneous case, we started calling that the characteristic solution. That has C1s and C2s in it as well, but those are constants of integration type thing. These C1s are just any arbitrary constants saying superposition principle. Okay. Now, I was just giving the homework exercises. I think I just finished doing that, and it got down to, I know I had said on 4.1.3, either 31 or 33 if those answers are in the back, and 35 if that answer is in the back. The discussion problems, very seldom have I found any of those in the back. If you find some that are, you can look at those. There's one other, as he said, right at the end of 4.1. Okay, so before we actually start solving homogeneous and non-homogeneous linear differential equations, we need one additional bit of theory, and that's 4.2. It's called reduction of order. Okay, it sounds like a pretty ominous thing, but it turns out being something that's not that bad, and it's very short. So that's why this would have been included in the video you saw, because it's very short. Okay, so here's what we got. In the preceding section, we saw that the general solution of a homogeneous linear second-order differential equations. Let me go on to a clean page. Is that okay? Yeah. Okay. All right. A sub 2, and that's a function of x, times y double prime, plus a sub 1, another function of x, times y prime, plus a sub 0, a function of x, times y, is equal to 0. The homogeneous or homogeneous case. Okay? We saw that the general solution of that second order is a linear combination. Y is equal to C1, make sure I got my thing, C1 y sub 1 plus C2 y sub 2. Okay? If you got a second linear differential equation, you're going to need two constants. Second order, you're going to need two constants. Now these are basically your integration constants. These are not arbitrary constants. These are your constants that you will come up with, and if you have boundary conditions, you can solve for. Okay. Now, where y1 and y2 are both solutions that constitute a linearly independent set. Now remember that too. This y1 cannot just be a multiple of y2 or some linear combination of y2. It has to be linearly independent from y2. Then these constants make sense. And you need to. If you had y1 was e to the x and y2 was 2e to the x, that's not linearly independent. Those dependent ones just double the other. So you need them to be linearly independent of each other. Okay. On some interval I. Okay. it says you're going to need blah, blah, blah. The basic idea described in this section is that equation 1, that right there, can be reduced to a linear first-order differential equation by means of a substitution involving the known quantity y1. Okay, I was trying to skip some of the reading here, but I don't think I can. Okay, beginning in the next session, we'll examine a method for determining solutions when the coefficients of differential equation are constants. That's where we're going to begin. Not functions of x, but constants. Okay? This method, which is a straightforward exercise in algebra, breaks down in a few cases and yields only a single solution, y1. It turns out that we can construct a second solution, y2, of a homogeneous equation 1, even when the coefficients of 1 are variable. That is, coefficients are variable. Okay. Provided we know that a non-trivial solution y1 of the differential equation. Okay. So basically we're going to use the first one, reduce that to a first order, is basically what we're trying to say here. The second set solution is apparent after the first order equation is solved. So this is called reduction of order. You go from second order to first order. But you got to find the y1 first. Okay? Suppose y1 denotes a non-trivial solution of that original differential equation up there. Okay? We seek a second solution, y2, so that the set consisting of y1 and y2 are linearly independent on the interval I. And if they're linearly independent, then their quotient, y2 over y1, is non-constant. Okay? Some other function of u, of x, some function u of x. In other words, y2 is some other function u of x times y1 of x. The function u of x can be found by substituting y2 is equal to u of x times y1 into the general differential equation. That method is called reduction of order. So blah, blah, blah. Let's see how we do it. Okay? Here's a solution. y1 is equal to e to the x. Pretty simple solution. It says, given that that is a solution of this, y double prime minus y is equal to 0 on the interval minus infinity to infinity. Okay? E's good everywhere. Okay. We need to come up with a second solution. But first, let's just verify. I think it's really easy to verify. y1 prime is equal to e to the x, right? And y1 double prime is equal to e to the x. So e to the x minus e to the x certainly is 0 for every variable x, value x from negative infinity to positive infinity. Pretty easy to verify that. Okay? But it's a second order differential equation. We need two linearly independent functions. Okay? Now, certainly 10 e to the x would still work, but that's just a multiple of this one. That's not linearly independent. Okay, 2 e to the x, anything like that. But if you start introducing e to the 2x, that won't work. Okay, it will not work. So we need a second solution. Okay, so what we're going to do here, to find that second solution, we're going to assume that it seems like they should start off y2, but they just say y, okay? I'm going to say y2, okay? y2, because that's what they set up above, y2 of x is equal to some new function u of x, and we don't know what it is, okay? Is equal to u of x times y1 of x. And we already know what y1 of x is. This is u of x times e to the x, because y1 was e to the x. Okay? Now, we're going to assume that u is that. Well, y2 is that. Well, let's see if it needs to also satisfy this differential equation, so we're going to need to know what y2 prime is, and that's going to be, product rule here, only let's use this one.
The derivative of u to the x.
U prime of x,
Dx.
e to the x, plus
X.
second,
Dx.
plus what? It's got to be u of x, e to the
There it
x.
is, yeah.
Right. Oh, I see. Okay, got it. You're doing e to the x first and then the second. Yeah. Okay. Yeah, it's derivative of the first times the second plus the first times the derivative of the second. That's how I was doing it. But yeah, same thing. Okay, well, looky there. We now have that's equal to u prime of x minus u of x times e to the x. Okay? I don't know if that's helpful, but I wrote it that way. Now let's do u to double prime. We need that because we have second derivative there. So now we got,
How did you come up with a negative u to 1?
I don't know. Okay. Had no idea whatsoever. It just didn't show up. I may have meant to put a plus and the plus didn't take. I don't know. Don't even recall. But there it is. Thanks for catching it. Would have been problematic later. Well, not really, because we're not going to use that. but anyway. So let's do the derivative of these. And we're going to use these products. So let's do it. You get me started here. It'll come back. I just had to bring it up a little bit.
Right, so the second derivative.
U double prime of x times e to the x plus
U prime of x.
u prime of x e to the x. That covers the first one. Plus, now the product rule here would be
U
prime of x e to the x plus
ux
e to the x. Got it. And now if we factor out the e to the x here, what do we have left? U double prime of x plus 2 u prime of x plus u of x. Now, I don't know if that's any better to write it that way or not, but it's a little bit shorter. Combined some terms and factored it out and that kind of stuff. All right, if we plug that back into our original and do our y double prime minus y, that's right up here. This is where we're going to plug this solution in. So this is going to be an e to the x times u2, no, don't know where that came from, u double prime of x plus 2 u prime of x plus u of x. Well, I shouldn't do that yet. All right. That's the y double prime minus, and the e to the x, the y here, y2 is here, that minus u of x, right? Okay. La-di-da, looky here. U of x's go out. They've been dating. No, never mind. Okay. They subtract away. So now that leaves us with, that is our differential equation, and we got that equal to 0. But here's the sort of strange news. you can rewrite this as, and this is your differential equation here, this y double prime minus y. And so y double prime minus y, which is supposed to equal to 0, is now here e to the x, which was our first solution that they gave us, okay, right there, our y1, times u double prime of x plus 2 u prime of x. Okay, and that's supposed to be equal to 0. Okay, so u double prime plus 2 u prime. Now, and this is supposed to equal 0. Well, e to the x can't be 0. It never is, anywhere, ever, okay? So that can't be 0, so that means this one has to be 0. That u double prime, I'm going to quit carrying around my of x's, that u double prime plus 2u prime is equal to 0. Okay. Now, here's where the magic comes to play. We come up with another function, w. Let w, and this is a function of x too, though I said I would quit putting it, but I just want to remind you it is, equal u prime of x. Okay? Then, w prime, that's the w prime of x, is equal to u double prime of x, right? It'll come back. Okay. So now, rather than this function, we have w prime of x plus 2w of x is equal to 0. All right. Well, now we've dropped from a second order to a first order differential equation. That's what we need to solve. Okay? Now, forget it started off being a u, we're now into w's, and that's only to the first order. Okay? Now, so there's that differential equation. It's a linear first order equation in w, and I'm completely out of room. So I'm going to erase everything here and only keep that formula in w. Okay? So here it goes. I'll probably need the original at some point, but I'll come back and get it. Okay? Let's go back to our w prime, I'm going to write it of x, plus, wasn't it? Yeah.
Plus 2.
Plus 2w of x is equal to 0. That's the differential equation we're now trying to solve. Okay? All right. Now, that is a linear first order differential equation in w, right? All right. So, what we're going to do is use our integrating factor. Remember, this is your p of x. Okay? And what you do with the p of x, you integrate the p of x. Integrate 2 dx. And that gives you 2x. And you never put a plus c with it. Okay? What do you do with that p of x? Integral of p of x? You do the e of it. Okay? E of the integral of p of x dx. Okay? And that gives you your integrating factor, e to the 2x. Now you multiply that by both sides, and you get e to the 2x w prime of x plus 2 e to the 2x w of x equals 0. All right. Now, if indeed that was your integrating factor, this thing right here should be a perfect derivative, d of the integrating factor, e to the 2x times w of x. If indeed that was the case, that should be that. Now, what I'm going to do is verify that's the case. If this is the perfect derivative of that, then this says that derivative of this, which would be, it's a product rule. So you like to do product rules, what would that be? Take a derivative of that.
2e to the 2x,
Okay.
wx, plus
Times w of x. Derivative of this times this.
yeah,
Right.
yeah,
Okay, so that's that term. Good. Plus,
plus e to the 2x
right?
times y prime over x.
Or, yeah,
y prime x,
w prime.
w prime x.
And that would be that. So yeah, sure enough that is. So if that's the case, that's a constant. So if derivative of that is 0, that means e to the 2x times w of x has to be some constant. Okay? All right. And they call this C1. I don't know why they do really, because it's only a constant, so C should work. Okay? So basically what we've got to do is integrate both sides here. And so this will be, sort of skipped a step there, put a dx over here, make it a differential. Okay? And the integral of,
Hang on,
yeah,
so you integrated it.
right. And the integral of a perfect derivative is just what's inside. Integral and does is a different derivative. And the integral of 0 is just going to be a constant. They call it C1. Maybe we'll see later why that's the case. So what is w of x? Is equal to C1 times e to the minus 2x. In other words, you divide both sides by e to the 2x. Okay, so there's your another solution. Okay. Now, reminding ourselves what the w is, remember w was u prime. Remember? Back on the previous. That is your u prime. So this means du dx. So let's take that and integrate it. So du is equal to c1 e to the minus 2x dx. All right. And if you integrate both sides of this, I'm going to leave my C1 on the outside, this gives you u is equal to C1, and what's the antiderivative of e to the minus 2x? E to the minus 2x, that's going to be there, and then unchain ruling it will be dividing by a negative 1, by a negative 2 basically.
I thought if we were integrating, we had to add one.
No, okay, wait. This is a power rule. This is exponential. Integrating exponential. If that was e to the 2, or e to the minus 2, yeah, you add, I mean, not e, x to the 2 or x to the minus 2, yeah, you add one when you're integrating. This is exponential. The integral of exponential is the exponential, but then you have to unchain rule it, which means, whereas when you're taking the derivative, you multiply by the derivative of the inner part. With the unchain ruling it, you divide by the derivative of the inner part. The derivative of the inner part is a minus 2 here. So this would be minus c1 over 2 e to the minus 2x. And then you would have another c2 here. So that's why they had the c1, because you have to have another constant here. All right. Now, so this is your u of x. Okay. Remember when I said I'd regret erasing all that? Now I do again, because remember, your y2 of x is equal. Okay. Whoa, whoa, whoa. Wait. He's here? All right. And he says, I'm always here. Okay. Okay. Muhammad is here. Okay.
He's the only one that's always here.
Oh, yes. Yeah, and he's always here ahead of you too, right? So, never mind. All right. Now, where we are is in 4.2, we're doing example 1, bottom of page 132. Okay. But you probably already saw the video, didn't you? You did? Okay. Shucks. That's
I didn't finish it.
Oh, okay. From my first, all 3 classes we've had today, a total of 0 students have watched the video. So if you even started it, you're ahead of the rest of them.
Last night.
Yeah.
Because I thought I was going to be the only one who didn't watch it.
Yeah.
So I said, let me start it and listen.
And it put you to sleep. Yeah.
I started watching and I just...
Yeah, I knew that was coming.
I started late, so
Yeah.
I was already...
Thank you for saying that. Okay, right. Like 1 in the afternoon. I'll put you right. Never mind. Okay, never mind. Okay. No, he didn't mean that. Okay. Now, if you recall, and Dan was just giving it to us, our y2 was u of x times y1 of x. Okay? Well, we got our u here. It's minus c1 over 2 e to the minus 2x plus c2. Okay? And we're going to take that and multiply it by our y of x, y1 of x, which, if my memory's right, was just e to the
Hang on.
2x, wasn't it?
Hang on just a second. I kind of got lost there.
Yeah, Muhammad does it every time. Okay.
Okay. All right.
And our y1 was e to the 2x, wasn't it? No. Yeah, I think it was. No, it's e to the x. Y1 was e to, right? Yeah, y1 was e to the x.
Yeah.
So this was e to the x. Okay, and when you multiply that through, what do you have? You have a minus c1 over 2 e, and when you do, this is 1 over e to the 2x, and you got a e to the x in the numerator, so e to the minus x plus c2 e to the positive x. Okay? Now, and that's what they get as your yeah. And this is your y. Remember, y1 is e to the x. So this is your constant with e to the x, and here's your constant. It doesn't need to be minus c1 over 2. You can make that a new constant, just c. So your solution set then would be, your y would be some constant. Call it C3, I don't care what you call it. C sub a. Okay, just call it something. E to the minus x plus some other c sub b e to the x. And those are obviously linearly independent solutions. So this one we got, this one we derived.
How did you deal with the C1 over 2, negative C1 over 2? How did you do that?
Okay, it's just a constant.
Oh, right.
Yeah, and it could be positive or negative, it doesn't matter. It's just a constant, so that's why I made it a new constant, C sub a, just to give it a different name, okay? And then the C2 was our CB, but who cares? It's just another constant. So those are just two constants, and those are linearly independent of each other. And you can do the Wronskian of them and show that indeed they are linearly independent. And so therefore those are our solutions. Okay, now. Okay. So that's how we did it, magic. You know, we kept manipulating until we reduced it to linear, then did, and then plugged back in, and we got our two solutions. Just remember the process, not so much the specific steps, but the process. Okay, now, this leads to what they call at the top of the next page, the general case. Okay, now remember we started, even though we never used it. Okay, it was kind of nuts. Remember, we called it a2 of x, y double prime plus a1 of x, y prime plus a0 of x, y is equal to 0. Okay, that was our original thing. And then they said in general case, suppose we divide the a2 of x, and remember, it can't be 0. If it is 0, it's not a second order differential equation. It's a first order, we do it completely differently. So a2 of x can't be 0, so therefore we can divide by a2 of x. So if we divide this by a2 of 8, we know that goes to 1. Divide this of a2 of x, we know that's going to be a legal thing to do. Divide this by a2 of x, okay? And we wound up with a y double prime is equal to plus, not equal to, plus this thing right here, we're going to call our p of x. It's just a a1 divided by a2. That's some function of x, y prime, plus, and this we'll call q of x, just to call them something else, y. That's equal to 0. Now this looks much closer to our linear. Remember back when we were doing first order linear differential equations, we had the leading coefficient here of 1, and we even called that back then was a y term, not y prime. And that was our p of x, and that's what we did our integration on, got the integrating factor. We're not going to do this now, but this looks a lot like this, only we have a third term there, q of x. Okay. Where p of x and q of x are continuous, that's required. Both of those are continuous. Now, to me that raises a big red flag that a2 of x, it better not, we already said it can't equal 0, but it can't have a factor equal to 0, because then the thing would not be continuous anymore. If it's a rational expression in x that had a 0 in the denominator, that's a vertical asymptote, so it would be continuous. So obviously it doesn't have that, can't have that, okay? Now, they're continuous on some interval I, continuous on I, whatever interval you're dealing with here, and y1 of x is not equal to 0, okay? Okay, well, that sort of makes sense. If that's a solution to this thing, you don't want 0 as a solution. In other words, a non-trivial solution. Y1 is a non-trivial solution, not the zero function. Okay, that was the other requirement we had before. Okay. For every x on the interval. Then we define, and this is just going over what we did, y of y, I wish they call that y2, but they just call it y, is equal to u of x. This is just reviewing what we've already done, y1 of x, okay? So y1 was some solution to this. We don't know what it was yet, but later we'll find it out. Then you go through the process of taking derivatives, y prime and then y double prime, and you get all the terms from the product rule, just like we did before, okay? And I guess we probably ought to do that. Okay.
How do you get to the, putting y equals to, or do you set every term into zero? Like
Okay, a little louder.
Did you set every term into zero to figure those out first? Like I already feel that y equals a of x, y.
Okay, where are you talking?
Where did you come up with the ux, y1 of x? Yeah.
Okay. All right. Number one. Okay. Start back up just a little bit. It's what we did before, so you weren't here then, so let's do it. They say here, let us suppose further that y1 of x is a known solution for this equation. Okay. Y1 of x, yeah, a known solution. We don't know how they knew, but y1 of x is a given solution, and it's not equal to 0. So it's a non-trivial solution. Okay, that's where we came up with it. Now to get y, I want to call it y2, is then multiply some unknown thing of x by y1 of x, which we know is a solution. Okay? So then let's take our derivatives. I know it looks like mystery meat, just pulling them out of the air or some undesignated body
I'm
part.
still not following you on that.
Okay, well, it's what we did before. It says, let's just imagine that we know one solution, y1 of x. Next section, we're going to see how to find those solutions. Right now, we just know we have a solution. y1 of x is a solution, but we know we've got to have two because it's second order differential equation. You've got to have two independent solutions. We've got one. Just like the last one, e to the x was a solution, but you couldn't come up with a second one that wasn't a multiple of it, and this is what the process we use. Let's just imagine there's some other u to x out there that a product of this times that is going to give us another solution. Okay? Well, if that is another solution, then let's take the derivative. The derivative would be product rule.
U prime of x.
U prime of x.
Y1 x.
Y1 of x. Plus. U of x.
Y prime
Y,
of x.
Y1 prime of x. Perfect. Okay? And then the y double prime is going to be
U double prime of
U
x.
double prime of x.
Y1 of x.
Y1 of x. Perfect. Plus
U prime of x.
U prime of x.
Times Y1 prime of x.
Y1 prime of x. Okay, that goes further. Plus U prime of x.
Y prime 1.
Y1 prime of x. Got it. Plus U of x.
Times Y double prime 1 of x.
Perfect. Okay. Now, All right. We're going to plug this into here. If I had more room, let's first see, we can combine these two like terms and make it two of those, right? Okay. And that's about all we can do to simplify. So let's plug it in. We have, for our y double prime, we have u double prime, I'm going to leave out the of x's, y1 plus 2u prime y1 prime plus u y1 double prime, right?
Right.
Plus p, I'll leave off the x there too, times a y prime, which is going to be u
Prime y1
y1 plus p u y1 prime.
Oh, you distributed the p?
Yeah, okay. Plus q, go back, okay. Q times y, which is u y1, right? And this is equal to 0. Got it? Okay. Now remember, y1 is a solution. So therefore, y1 double prime plus p times y1 prime plus q times y1 is equal to 0, right?
Oh, say that again?
Okay. Okay. What I'm going to do is get all the terms,
Oh, I see what you're saying.
all the terms with just a u in it and put them together. Okay? So we have a u double prime y1 plus 2u prime y1 prime plus, now, u times y1 double prime plus p y1 prime plus q y1, right?
All right, hold up right there.
Huh?
Hang on.
I pulled off this term, and that term,
Okay,
and put them together. Those with just u in them, and factored out the u, right? Okay, and I've still got one more term left, plus p u prime y1. That's equal to 0. By that, I just rearranged the terms and pulled these out. But we know this thing right here, that is exactly this with y1 plugged in, and we know that's the solution. So if that's the solution, this is 0, right? All right. I wish I had more room at the bottom. I don't.
But remember earlier you took up the x. So what happened to the x?
You just got tired of writing. You just got tired of
Yeah,
writing.
of x, if I'd have put of x's in there, I'd have gone somewhere down the wall there.
They're still there.
Yeah.
Just imagine.
Then all these are functions of x's.
I just wanted to make sure you did just like.
Yeah. I didn't, yeah.
You don't need no x's here.
These are all functions of x's. Every one of them. The p's, the q's, the y1s, the u's, the u primes, the y1 prime. All of them are functions of x's. I just didn't have room to write them all. But we do have that this is equal to 0. Okay? So this whole term is equal to 0. So let's shorten that to be what we have left. U double prime y1, so aggravating, plus 2u prime y1 prime plus p u prime y1 is equal to 0. By that? It's this term, that term, and that term. Right?
Well, then we have the exact same scenario.
Okay, except, no, we see that has what we have here the scenario we have here is we don't have the U term. The U term went away because we got all those here, and that was equal to 0. So this one went away. So here we have an equation that's only functions of U double prime and U prime. No U's. Now all functions of X's, got it, but no U's anymore. So therefore, since U's not there, we're going to come up with a good old W, which is W is equal to U prime. Okay? This is how we reduce. Okay?
And then it takes it down to a linear.
And it takes it down to a linear. That's what we're doing here. Okay? Yep. I want to make sure they still called it W. So W is equal to U prime. So then W prime is equal to U double prime. So now our thing is W prime Y1 plus 2 W Y1 prime plus P W Y1 is equal to 0. Okay? All right. Now, let's get the Y primes together, and there's only one, W primes together, there's only one. This is Y1 W prime plus, and the W terms are 2 Y1 prime plus P Y1 times W. That's equal to 0. Okay. Now, that's now a linear equation. Well, yeah, it is. But it's only in terms of, make sure I've got it written right, yeah. It's linear and separable. Now,
Hang on just a second. You factored out a Y1. Is that correct?
no, I factored out a W from the two terms of W. These two terms. Factored out the W. Left the 2 Y1 prime and the P Y1.
Okay. All right.
Left that one alone because that was a W prime.
Yeah, that's what was throwing me off because I'm sitting there looking up and nothing's changed. Okay.
Yeah. Okay. Now, I need room. I need room. Okay. And I sure hope I don't need this anymore. If I do, you've got it, right? But if not, I'll look in the book and find it. I just need more room. Okay.
Yeah, I think I got lost at that point.
Yeah. Well, we'll go back and get it if we need anything from the book. But you see, we've eliminated most of this, so I don't think need it anymore. But I just need the room desperately.
Oh, by the way, it's time.
Oh, is it? I knew we must be running out.
How close to being done are we? We got them waiting for them.
We got a little bit to go, but what I'll do, got it in my pocket here. What we'll do, you got your notes, and as far as I can tell here, we're down to 4. We've got 4 done. So we'll start after 4. Okay. So this is a very short section. We'll finish it next time. But I don't know that we've got enough done that you can do any homework exercises till we finish this and do example 2. So we'll hang on and do that. So no new homework exercises there. But next time, which is Wednesday, we will finish 4.2 and finally get to doing 4.3, which is homogeneous linear equations with constant coefficients, and then we won't be having them telling us we got a formula. We're going to find our own solutions.
Good.
Yeah, sort of like we did back finally in chapter 2, wasn't it? When we finished all the 1 stuff, we finally were able to solve things in separation equation, linear, blah, blah, blah. Now we're going to actually do, we'll start with linear, with homogeneous or homogeneous, then we'll do non-homogeneous. We'll choose which way we go after this, but yeah, we'll go from there. All right, good deal.
I have my research paper